Hi, my name is Suraj Matthew Thomas, and this is my midterm submission for SIG 718 Real World Analytics. So let me go ahead and share my screen. Let's go into presentation mode. Okay, so now the data set that is given is the energy appliance data set, which tells us how much of energy is consumed by these appliances based on a set of input data. So the input data is X1 to X5, which goes by the temperature of the kitchen area, humidity of kitchen area, temperature outside, the weather station, humidity outside the weather station, visibility from the weather station, and finally the target variable, which is Y. Okay, the sample size that was given is 671 observations. But as we go along, when we do this data analysis, we have reduced the sample size to 340 for our analysis. Now, we did an exploratory data analysis of these 5 variables and the target variables by seeing how the data is distributed using a histogram, and also the scatter plot between each of the variables and the target variable, which is 5. Now, if you see X1, X2, and X4, right? X1, X2, and X4, these are the variables. What is that? Temperature in kitchen area, humidity in kitchen area, and humidity outside. All look normally distributed, like all the histograms almost look normally distributed, but then we need to do a KS test to find out if there is this light skewness that is there. We need to test. So the KS test reveals that for X1, X2, and X4, the p-value is greater than 0.05. So it can be approximated to the normal distribution. You need not do any log transformation or polynomial transformation for this. It can be approximated. If you see the scatter plot of these, the scatter plot also shows that there is a positive relationship. Though it doesn't show much of a pattern, there is positive relationship between each of these variables and the target variable. So that was for X1, X2, and X4. Right now, let's go for X3, X5, and Y. X3, X5, and Y, right? So X3 and X5, the p-value is less than 0.05, which means that there could be some skewness. So we tested for skewness and saw that for X3, it is 0.09, which is less than 0.5, and that indicates moderate negative skewness. But for X5, if you see, the skewness is 0.71, which is greater than 0.5. Therefore, it has moderate positive skewness. And for Y, though the p-value is less than 0.05, it can be approximated to a normal distribution. But when you test for this, the skewness is 1.7. It's highly skewed, highly positively skewed, right? So we need to see what needs to be done and what are the transformations that we need to apply. Now, the summary of what I said in the previous slides are given here. The p-values were found using the KS test, which is the Kolmogorov-Smirnov test. If you see X1, X2, and X4 greater than 0.5, X3 0.05, and X3, X5, and Y is less than 0.05. So we might need to add these, do transformations for these X5, Y, and X3. X4, X2, and X1, you need not do anything because no log transform. It can be approximated to. No negation because it is not, no negations needs to be done. No log transformation, polynomial transformation needs to be done. Now, when we test for skewness, right, when the skewness is done, we find out that X5 and Y, which is greater than 0.5, are positively skewed, and hence we need to apply log transformation for them. All the others are falling within the range, so we can say that it can be approximated to normal distribution. Moving on, we need to select 4 variables out of these 5 variables to do our further analysis. Now, how do we select these 4 variables? Is through the correlation test. We did both the Pearson correlation test and the Spearman correlation test. In the correlation test, we found that X3, that is temperature outside the weather station, has the highest correlation, both for Spearman and Pearson. And the weakest correlation is humidity outside, 0.1 here and 0.07. So it makes it clear that the others have correlation, but they are moderately correlated. So This makes us clear as to which one we need to omit. So what we have omitted is X4, which is very weak correlation. The others which has correlation, high correlation, X1, X2, X3, and X5 are the 4 selected variables. Now we will do transformation on these variables, right? Now, how do we do transformation? Now we have to do log transformation, right? X5 and X5 and Y. Okay, we need to do log transformation. So what we do is we first do log transformation for those 2 variables and do min-max transformation for the entire set, that is X1, X2, X3, X5, and Y. Okay, for all we do the min-max transformation so that everything is under the same interval 0 to 1, and it makes it easy for us to analyze, inference, and go forward with the analysis. Now, after applying transformation, log transformation for those 2 variables and min-max transformation for the selected and the target variable, when we apply, you can see everything has come to a normal distribution. Now, if you check for skewness here, it will be almost no skewness, very mild skewness will be there, but then it is almost, you have transformed the variable to a normal distribution. Now, model fitting. Now, for model fitting, what do? We have been given 5 models, that is weighted average mean, weighted power mean with P is equal to 0.5, weighted power mean again with P is equal to 2.0, then order weighted average, and the Shokit integral. Now, when we run this, when we fit the model, you can see that the Shokit integral has the lowest root mean square error. So this is our model of choice. Why only don't see new root mean square error? We also see the average, absolute average error, which is the lowest. The Pearson and the Spearman correlation, the correlation between them is the highest among all the other variables. That's why it's highlighted in green. So this is my model model that I'm going to select for further analysis. Now, if you see the weights also, if you see, W3, so W1 corresponds to X1, W2 X2, W3 X3, W4 X5, because we omitted X4, W5 X5, and then the orness. Now, if you see the weights also across all the models, if you see W3, weight 3 has the highest. So the importance for X3 is the highest. What is X3? I think it is temperature outside the weather station. Okay, so that is the highest importance, and the lowest importance over here is W2, which is X2, which is humidity in the kitchen area. Okay, so that is the lowest importance because the weights are minimal. Okay, except for OWA and a Shokit integral, which is also, if you see, it is minimal among them. Okay, so it has the lowest. So now, why did we select Shokit interval? Why? Because it had the lowest RSME and the highest Pearson and Spearman correlation. So Shokit integral model is chosen over the other models. Now, if you see for correlation analysis, right? So what we have done is X3, like here, has the strongest correlation. Okay, X3 has the correlation, has the strongest, okay, and strongest relationship from the correlation analysis. And more importance of weight should be assigned to the third variable to perform better. Okay, so the third variable, because the weights are the highest over here in the third variable. Right, so the reason why this would be a little bit over here, see the weight over here is in W4. If you see the RMSC also is, if you see the RMSC is also on the higher side. So maybe it's a poor performing model, and that's why the weights have not been allocated properly. Okay, so now let's move on. Now, choosing the best model, like I said, Shokit integral model. Now, they have given us new data to check on the Shokit integral model as to how it is going to perform. Now, the new data has been 22, 38, 4, and 34, which is X1, X2, X3, and X5. Now, this has to be transformed using the log transformation and the min-max transformation. And the data has been transformed to an interval of 0 to 1, and that's why you get this transformed variable. Now, we need to predict. So the model has gone into the prediction state. Now, when we apply prediction, if you see the predicted value of Y, that is the energy consumed based on these inputs, is 82.95. And the energy value that is observed, the given value is 100. So which is a pretty good prediction. I mean, it's close, it's not very close, but 82 and 100, I would say it is a pretty fair prediction. So it is performing well. The model is performing well. So X2, like I said, has the least importance. X3 has the highest importance, and X1 and X5 has the moderate importance. If you look at this particular table, weights and parameters table, right? Now, therefore, if you need to get a low energy in an appliance, the way in which the weights should be applied, the input should be at the lowest at X3, the lower values in X1 and X5. So if you see low visibility, low temperature outside, same humidity, because X2 has no weightage at all. For more, has the least weightage, same humidity, it yields a low energy use of the appliance. Now, we've done a linear model versus the Choquette integral model just to compare how the residual standard error is performing against the Choquette integral's root mean square error. So if you see, it is almost similar. If you see RSC is 0.159, the linear model, and 0.154. Yeah, the Choquette integral is performing a little better. I mean, very, very, very mild performance. But then the linear model has its own pros and cons. The Choquette integral also has its more pros and cons. And this is scatter plot is shown between the linear model, original and the predicted values. This is for Choquette integral, original and the predicted values. The linear line that goes across. The plots are shown over here. Now, if you see the linear model, we have the standard error R square, adjusted R square, P square, PP value, which is less than 0.05, and the F statistic value. Now, the residual error is very small, 1.593. So if you see, only 36% of the variance in Y can be explained by the independent variable. So this can be informed by the adjusted R squared value. So the adjusted R squared, like you say, it is a good measure to evaluate the model performance. Having this measure is an advantage of the linear model of the over the Choquette model. Now, if you see linear model versus the Choquette integral model, the p-value is less than 0.05, which indicates that the model is statistically significant and has a good predictive power. I'm talking about the linear model. Okay, and when it comes to the linear model, there is assumptions of, homoscedasticity, the linearity, the normality, and the independence of the errors. So the relationship between the predicted values for both linear and Choquette are positive and strong. But linear model has, it has a little bit of advantage, saying that it can exhibit unbiased estimation of the model performance as compared to the Choquette model. Now, if you compare the predicted values of between Choquette and linear integral model, see if you see that they are performing almost the same. The linear predicted value and the Choquette predicted values across the linear line. See, if they are almost the same. I mean, there is very minimal difference if you see these overlaps that are happening over there, right? So this is what I wanted to cover, okay? And this is my submission for the midterm assignment. So the Choquette integral model, in summary, is the best model. We've also, done the preliminary analysis, then the transformation, and after the transformation, we have fitted the model. Once we have fitted the model, we have introduced new data or unseen data, see how the model is performing, and then we compared the Choquette integral model with the linear model, and we done our analysis. So thank you.